Welcome back to BrainyBox, where we venture into the mind-bending mysteries of the universe. Today, we're plunging into one of the most perplexing phenomena in the cosmos: black holes. These cosmic giants twist our understanding of space, time, and the very fabric of reality. Imagine a region in space where gravity is so intense that not even light can escape. Once it crosses the event horizon, the point of no return. For decades, black holes were the stuff of theoretical physics, proposed by Einstein's general relativity in 1915. But now, as we reach 2026, they're no longer just abstract ideas. They're real, they're everywhere, and they are rewriting the laws of the universe. Let's start with a mind-boggling discovery straight from the headlines. In January 2026, astronomers using the Subaru telescope uncovered a supermassive black hole that's breaking all the rules. This monstrous entity, located just 12 billion light-years away, is growing at an unimaginable speed, 13 times faster than the so-called Eddington limit, once thought to be the maximum rate a black hole could consume matter. This cosmic leviathan is gobbling up gas at an incredible rate, sending out blinding X-rays and a powerful radio jet. It suggests that black holes in the early universe may have evolved in ways we could never have predicted. And this is just one of the many lurking in the depths of space. In fact, our very own Milky Way is home to millions of these beasts, with the nearest one, Gaia BH1, sitting just 1,500 light-years away, silently orbiting a star like a cosmic parasite. But black holes aren't just cosmic vacuum cleaners. They're also reality-bending time machines. As you fall towards one, time itself slows down for you relative to the outside universe. A second near the event horizon could feel like centuries passing in the universe beyond. And if you fall in too far, say into a stellar mass black hole, you're in for a fate called spaghettification. This horrific process would stretch your body into a thin noodle as tidal forces tear your atoms apart. This isn't just science fiction. These are the mind-blowing facts supported by over a century of math and observation. From gravitational-wave observations from LIGO and the breathtaking images captured by the Event Horizon Telescope. And yet, black holes still hide deeper secrets that could lead to a unified theory, or even open a doorway to wormholes. Stay tuned for Part 2, where we'll explore how these cosmic monsters form and why some grow to billions of solar masses. Black holes might just hold the key to understanding the entire cosmos, and you won't want to miss it.
The universe doesn't just hand out black holes. It forges them in the most violent, catastrophic processes imaginable. Understanding how black holes come into existence is key to unraveling their mysteries, because the way they form determines their size, behavior, and future fate. Let's break it down step by step, because each step of a black hole's birth is a crucial part of its cosmic journey. Most black holes we observe today are born from the explosive death of massive stars, a process known as stellar collapse. When a star with at least 8-10 times the mass of our sun exhausts its nuclear fuel, gravity takes over. The star can no longer sustain itself against the overwhelming pull of its own mass. In mere seconds, the core collapses, triggering a supernova explosion that sends the outer layers of the star flying through space at millions of kilometers per hour. If the remaining core is large enough, there's nothing strong enough to halt the collapse. Even the pressure from the neutrons can't fight against it. The core keeps collapsing, shrinking past the neutron star phase until it reaches the ultimate point, a singularity, a point of infinite density. At that exact moment, the event horizon forms, the invisible boundary where escape velocity equals the speed of light. Anything that crosses this boundary is lost to the black hole, never to return. These are known as stellar mass black holes. But that's just the beginning of the black hole saga. In the early universe, black holes formed in a dramatically different way, and on a far grander scale. Recent breakthroughs from JWST and Chandra have revealed supermassive black holes already existed just 500–700 million years after the Big Bang. How could they grow so rapidly, far faster than we ever imagined? Research is focusing on 3 groundbreaking theories. Direct collapse. Enormous gas clouds in the early universe collapse directly into black holes without ever forming stars first. Heavy seed black holes. In ultra-dense clusters, massive stars underwent runaway mergers, creating intermediate mass black holes. These black holes then rapidly grew by swallowing surrounding gas and merging with others. Primordial black holes. Tiny black holes that may have formed from density fluctuations in the moments just after the Big Bang. And the 2026 breakthrough. Astronomers have observed the quasar J0529-4351, one of the brightest objects ever found. Growing at an astonishing 40 times the Eddington limit, this discovery shatters previous models of black hole growth. These massive gas flows could be funneled by galaxy mergers or vast cosmic filaments. Every massive galaxy has a supermassive center, including our very own Sagittarius A at the heart of the Milky Way, with a mass of 4.3 million solar masses. These behemoths are essential architects of galaxy formation, regulating star birth through powerful jets and radiation. These jets heat surrounding gas, preventing it from collapsing into new stars, effectively controlling the rate of star formation. Black holes are fundamental to the structure of the universe, shaping galaxies and the very nature of space itself. The more we uncover, the more it seems these cosmic titans are the architects of reality. Subscribe for more cosmic truths. I'll see you in the next one. Now, let's get personal. What happens to you, a human being, if you fall toward a black hole? The answer is a mix of grotesque horror and awe-inspiring physics. It all starts with spaghettification, a gruesome process where the black hole's tidal forces stretch and tear you apart long before you reach the center. Gravity is not the same everywhere around you. It differs depending on where you are in relation to the black hole. Near the event horizon, gravity pulls much stronger on your feet than on your head. In a stellar mass black hole, say one with 10 times the mass of our Sun, this tidal difference becomes lethal miles outside the event horizon. Your body stretches vertically while being squeezed horizontally. Your atoms will tear apart, and you'll be reduced to a stream of plasma racing inward toward the singularity. However, things are a bit different if you're falling into a supermassive black hole, like Sagittarius A at the heart of our Milky Way, which weighs in at 4 million solar masses. The tidal forces near the event horizon are much more gradual, so you might pass through it relatively intact before spaghettification kicks in. But once you're deeper inside, closer to the singularity, the tidal forces will tear you apart with a vengeance. Here's the truly mind-blowing part. From your perspective, you don't feel the stretch as pain. Because of the equivalence principle, the destruction happens so quickly that your nerve signals can't travel the length of your body before it's all over. You wouldn't even register the agony in the conventional sense. It's a bizarre and unsettling form of weightlessness, even in the face of annihilation. Now, brace yourself for the next cosmic twist: gravitational time dilation. As you approach the event horizon, time begins to slow down for you relative to an observer far away. 1 second on your watch might stretch to years, centuries, or even eons for someone watching from a safe distance. NASA's 2024-2026 supercomputer visualizations simulate this. As a camera falls toward a black hole, the entire universe ahead compresses into a shrinking, brightening circle. The black hole's accretion disk warps into multiple photon rings, light bending around it several times, creating eerie mirror images and duplicates of the disk. By the time you reach the event horizon, the sky above you collapses into a single point, and from the outside world, everything seems to freeze in place. But from your perspective, the journey is far from over. While distant observers never actually see you cross, they only watch you slow down and fade. For you, the plunge happens in finite time. Recent updates in 2026 simulations show that for rotating black holes, known as Kerr black holes, space-time itself is twisted. This twisting, known as frame dragging, drags both light and your path into a vortex, making the experience even more bizarre. Mind-blowing 2026 update. New observations from JWST of little red dots suggest some black holes form so violently that the infouling matter experiences extreme time dilation during their birth. This means that the singularity might not just be hidden, but that relativistic effects stretch the final collapse across cosmic epochs from the inside. Crossing the event horizon isn't the end of physics. It's the point where general relativity breaks down entirely at the singularity, where infinite density and zero volume coexist. Quantum gravity theories like string theory suggest the singularity might resolve into something finite, like a fuzzball, hinting at a new level of understanding. Falling into a black hole isn't just violent, it's where the fundamental laws of the universe break down. Stay sharp, I'll see you in the next one. Black holes aren't the eternal tombs we once thought them to be, they actually leak. In 1974, Stephen Hawking made a groundbreaking discovery by combining quantum field theory with general relativity. Black holes emit radiation. This radiation, now known as Hawking radiation, arises from quantum fluctuations near the event horizon. These fluctuations create particle-antiparticle pairs. One falls into the black hole, the other escapes. To an outside observer, the escaping particle appears as real thermal radiation coming from the black hole itself. The temperature of this radiation depends on the mass of the black hole. Smaller black holes are incredibly hot and evaporate in fractions of a second, while supermassive ones like Sagittarius A are much cooler, colder even than the cosmic microwave background. These massive black holes will take longer than the entire current age of the universe to evaporate. For Sagittarius A, this is around 10 to 67 years. But here's where it gets mind-blowing: the black hole information paradox. Quantum mechanics holds that information can never truly be destroyed. Every process is reversible, and information is theoretically recoverable. However, when a black hole evaporates, the radiation appears completely thermal and featureless, carrying no trace of the infalling matter. This creates a fundamental dilemma. If the information is lost, it violates the principles of quantum mechanics, putting the foundations of physics into question. Hawking initially argued against the survival of information, but by 2004, he conceded his bet. The holographic principle suggests information might be encoded on the event horizon, like a 2D hologram projecting a 3D reality. Other ideas include soft hair on the horizon storing info, or the controversial firewall that destroys anything falling in. Recent breakthroughs suggest that after half of a black hole's evaporation, information begins to leak out, resolving the paradox. 2026 is proving to be a crucial year in accelerating this debate, with several major milestones. New calculations using wormhole replicas have provided strong evidence that information escapes after half of its entropy is reached. In 2026, JWST and the upcoming LISA detector are investigating primordial black holes as dark matter candidates. Just this January, Nature Astronomy found tentative evidence of information leakage in the X-ray spectra of hyperaccreting quasars. These breakthroughs suggest black holes may be the universe's ultimate quantum computers, encoding every bit of information. If true, this could bridge the gap between quantum mechanics and gravity, providing a key clue toward a theory of everything. Stay tuned for Part 5, where we'll dive into wormholes and dark energy. Subscribe to stay sharp. I'll see you in the next one.